Hello and welcome to sections 21.1 through 21.2. In this video we'll be going over moments of inertia, products of inertia, parallel axis theorem, parallel plane theorem, and then solving for the product of inertia for a simple shape in example 1. So let's start off by writing down moments of inertia. So these are mass moments of inertia, which you should remember from our planar rigid body analysis. Alright, so if you remember, we have Ixx. It is going to be the integral of r squared dm, so the radius after some piece of mass. We can rewrite that in 3 dimensions. The radius will be, so in 2 dimensions, it's a little different, but in 3 dimensions, we just get y squared plus z squared to get our radius, dm. And then Iyy and Izz look the same, so I'll write those out and then bring you back. Alright, and I forgot to put an x up here, by the way. So, Iyy is just the radius about y squared, Izz, radius about z squared, which is x squared plus y squared, and then x squared plus z squared. So, things that you have basically seen before. I believe in our 2D ones we just did the r squared. We didn't actually expand it out. Now if we get things that are man-made, they may not be continuous. We may not want to do an integral, so we can do things with composite bodies. And in that case, we want to use parallel axis theorem. So you should be familiar with this. Again, we did this with our planar rigid bodies. So again, in the x direction, so if I wanted to find Ixx about some arbitrary point, then that would be equal to that Ixx through the center of gravity plus mass, and then we would want to do Rx squared here, but I'm just going to save us the time. So we would do delta y squared plus delta z squared. And if you put that together, you'll get delta Rx squared. Okay. So again, I'm going to write out the other two for yy and zz and be right back. Okay. So again, just remember in 2D we just had Ix about any point equal to Ix about the center of gravity plus mass distance squared. And so because we're now 3D, we now get our distances using using Pythagorean theorem here. It doesn't matter if these distances are positive or negative because you're squaring them, but in general you should put them in as positive or negative based on the coordinate system. Alright, so that should be mostly review. All we did is we expanded these out for 3 dimensions. So the new property is products of inertia. So moments of inertia, if you remember, so the mass moment of inertia, that was the resistance to angular acceleration. Products of inertia are a measure of symmetry. How symmetric is the body about a plane? This is the best way I can think of to describe it. So we're going to get, and so you might have noticed that we have an xx here and a yy here, and in the past you might have seen it as just ix or iy. Well, for products of inertia, we're going to get something called ixy, and it is equal to iyx, and we find it by integrating the mass, and we take x times y, and then dm. So if you have some continuous shape or curve, you can find its product of inertia by integrating from your your base point, A, O, G, wherever your coordinate system sets, out to your differential piece of mass in the x direction and the y direction, and you multiply them together. So this looks a lot like what we're doing up here. We're doing an r squared dm, so we're kind of doing a similar thing here. If this was x and x, I would just get x squared dm, which would be this thing here. But instead of doing x and y. So this is similar in form, but it's different. So again, I'm going to write out the other ones, and I'll come right back. Okay. So we have IXY, IXZ, and IYZ, and you can flip them, so XZ can become ZX, YZ can become ZY. They are equal to one another. And then you just find them. If it's a continuous shape, you can just integrate. But a lot of times, again, our man-made shapes don't integrate nicely. They have sharp angles and stuff like that. So instead, we can use our composite bodies. So we had parallel axis theorem for our mass moments of inertia. We have a similar idea here, but instead of an axis, it is a plane. So again, these are planes. This is the XY plane, the XZ plane, the YZ plane, and I'm looking at symmetry in that plane. That's what that means. Here, I'll pause real quick. So say we had say we had some body here. If I could cut this in half so that it's symmetry, I would cut it right here, and then I would cut it right here. And so this is now symmetric about this axis and this axis. So if you call this X and you call this Y, it's now symmetric about both. In that case, it's IXY would be 0 because it is symmetric in this plane. If you kind of wanted a really quick definition of what that is. Allows us to work with man-made shapes. So IXY about any point A will be IXY about through the centroid. So it has to go through the centroid. And a lot of times, again, if you can make it such that so we could have just as easily oriented these axes poorly. So I could have oriented them, say, this way and this way instead, and then it's no longer symmetric, and I'll get some non-zero number, even though I'm still at G. So if you can orient this such that you get 0 here, it makes this a lot nicer. So that's one of the things we'll look at doing. So the product of inertia in the XY plane, and then mass times, so we can use, I believe, let me pull it up over here. Yeah, so we have a dx on there, so I'll just use dx, so I'll just use delta. So delta x and delta y. So how far away are we from the center of gravity? Distance from G. So we're measuring from G. And we do want to include positive or negative. So if it's negative, make sure you make it negative. If it's positive, make sure you make it positive. So sign matters here. Okay? So again, I'm going to pause the video. I'll write out the other two. And here they are. So just remember, IXY is the same thing as IYX, so I'm not going to write out the other 3 versions of this, which is just the XY flipped, and the XZ flipped, and the YZ flipped. It's the same thing. But it looks a lot like parallel axis theorem, if I bring that back down. So if we just kind of look at, you get about an arbitrary point, about G, mass, and then basically we're squaring some distance. So if these were both delta x's, we would just get delta x squared, but instead we're getting x and y. So you can kind of see the pattern of where this comes from. And again, our goal here is if we can find so we find the center of gravity, and then we want to orient our axes so that we have symmetry, then this term goes to 0. We find the mass of the shape, then we can just figure out how far did we move away from the center of gravity in the x and in the y. And if you notice, you can move along just one of these. So you can just move just on this or just on this, and this will still be 0. All right, so now let's jump into example 1. Okay, so this is example 1 copied down. We're trying to find IXY, so the product of inertia in the XY plane for this 3-dimensional shape. We are given that rho is 490 pound per cubic foot. So one of the things you can do is, because this shape is the same height all the way around, we can make it easier by just drawing it in the XY plane. So the first thing I'll do is I'll just redraw this in the XY plane. So in this case, this would be our X. In this case, this would be our Y, so don't get too confused. And then we have our dimensions, so I'll just quickly mark out that this is 0.5, and this is 0.75, And hopefully you can see what the rest of the dimensions are. I'm not going to take too much time to do that. We can make this shape. So again, composite bodies are the idea of we want to make simple shapes and then combine them to get to this shape. So we can make a big rectangle and then subtract this. There's this box here that is 0.25 squared. So 0.25 and 0.25. So I can subtract that box out of that and make this shape. That makes it a lot easier for us. So we're going to make a big rectangle, and we're going to subtract a little square. So this is going to be 0.25 and 0.25. This is going to be 0.75 and 0.5. So rectangles and squares, really easy. So making our life easy. And so what we're going to have here is we're going to have some IXY prime minus some IXY double prime to get our IXY. That's our goal. So you might know this is superposition. So we're going to just kind of do it in pieces, put it back together. We've been calling it composite bodies. Same idea. All right. So IXY prime. So this is the XY prime body. That is going to be about that point there. So just to keep in mind, our axes are over here. And so for this one, the axes are over here. And for this guy, the axes are out here in space, technically. So we're some distance away from those axes. So we're going to, first we want to find it about the centroid. So we want to find IXY prime about G. And then we want to go mass, and then delta X, delta Y. So that's our parallel plane theorem that we had from last time. We would like this to be 0. To make this 0, we need to determine which orientation. So we want to keep it the same directions. That is important. These have to be parallel. So I can't go and make some new axis that points some other direction. So conveniently, our parallel axis here does cut it in half. So if I kind of continue this way, we can see that the top half and the bottom half are symmetric. If I continue this way, we see the left half and the right half are symmetric. So that's our new X and Y. So remember, X is down in this case and Y is over. And if you really don't like that, just rotate your paper and voila. All right? Same thing here. We're going to stick this at G. We're going to have a coordinate system. We're going to have our X and our Y. And you can call this X prime, Y prime, X prime, double prime. So you can use all your primes and whatnot. All right. So for this one, because this is symmetric about this plane, this zeroes out. The mass of this thing we'll find in a little bit. So this is mass. This is the mass of the entire thing. I'm going to call this mass prime. To get up to here is going to be half of this distance. So it's going to be a negative. Make sure just sign matters. So we're going to go negative in the x. So it's negative 0.25. And then to get over this way is going to be a negative 0.375, which is just half of 0.75. And so all we need now is the mass. So let's find that mass prime. So it's going to be rho times v. Rho is 490. The volume is just base width height. So it is 0.75, 0.5, and then it is 0.25 tall. So let me throw that in a calculator, get a number for you. So you'll get 45.94, but that's weight. So we have to make sure we divide both of these by 32.2. Because remember, this isn't quite density. So density is not the right term for this. This is specific weight. It's 490 pounds per foot cubed. So not quite. So divide it by 32.2, you'll get 1.427. Okay. So then you plug all the, you put your 1.427 here, run your calculation, and you'll find that IXY prime about our base point A up here is 0.1338. And then we repeat the process for IX double prime. IXY double prime, about that same base point A up here. So we're going to find it about IXY prime, double prime, about its center of gravity plus its mass, delta x, delta y. Alright, so mass 490 over 32.2 times volume. So the volume, so this is just a 0.25 cube. So it's just 0.25 cubed. So it's actually a cube, which is actually really nice. Delta x, so this is our not quite rho. This is our volume. This is delta x. So delta x, so this, to get this thing up there, so conveniently it lies on this line as well, so it's also going to just be half of this distance, so it's just going to be 0.25 as well. So negative 0.25. And then our delta y, so y being this direction, so this is going to move a little bit further. So it's going to go, so this distance here is 0.5. So it's going to go to 0.5 plus the half of this, which is 0.125. And so that is a total of negative 0.625. And if we orient our axes like we've shown, this zeroes out because we're symmetric about the y-axis, symmetric about the x-axis, so we're symmetric in this plane at G. Calculate IXY double prime at A is 0.0371, and we'll keep it 4 to sig fig 5. Alright, so all we have left to do is find this. So we know that this is 0.1338. We're going to subtract a 0.03715. We can do that again because we found everything about the same base point A up here. So then our total is 0.09665. Our units are slug feet squared. So I'll just rewrite that again up here. So IXY is 0.0966 slug feet squared. Alright, so you can do this in other axes as well. Same thing. So we have our 3D shape. Since I had the same height, we chose to redraw it in 2 dimensions to make it easier. So we only had to find it in the XY plane, so I just drew it in the XY plane. We use composite bodies by splitting it up into a big rectangle and a small square. We found the IXY about the center of gravity for each one to be 0 by orienting our axes such that they were parallel to this, and they cut the thing in half. So it's more important that they cut it in half, but there's a couple things going on there. They have to be parallel, otherwise we can't do parallel plane. And then it has to go through G. So we really didn't have a choice, but conveniently it ended up such that it all worked out. Then we zeroed those out. And then we just use our mass, delta x, and delta y for each one. All right. Hopefully that helps. If you have any questions, feel free to reach out.